course, for exam 1 or up, scores are all over the place. Some did quite well. Some were at the other end of the spectrum. Some in the middle. But for those at the other end of the spectrum, those in the middle, those who did quite well, there will be ample opportunity in remaining quizzes and exams to boost up your point accumulation considerably. I say this because if you didn't fare well, do not despair. There's no reward in quitting. The opportunity will always be there. But you, I'm sure, understand that it's your job to materialize the opportunity. It doesn't happen by magic or by wishing. See us as necessary for assistance. Please, when I post the key, take note in particular of the questions which are marked most commonly missed, because it is my policy to revisit many of these questions on the next exam, to give you the chance to get the material, and by responding correctly to tell me that, yeah, you got it. That's what I want. And as I'm sure you also recognized, I don't give any questions which are jeopardy. I'm not interested in me giving you a piece of information and you give it back. That's monkey business. Each and every question and problem will demand analytical thought. It's the only way I can get you to understand, because that's where it's at. But you know this. Now, we proceed with analysis of Bronsted-Lowry acid-base equilibrium systems. And take a look at the final consideration of which we need to be aware in order to take any water solution and analyze it in detail so as to, if we wish, quantitatively inventory for every species in the system whose existence is dependent upon pH. And that is usually most of the species in the system, if not all. So this is an important aspect of what you have to have in your bag of tricks to analyze solutions, water solutions, from an acid-base standpoint. The lead into this consideration is brought to us by our 100th molar to 2 significant figures iron nitrate solution, which we began to talk about last time, in which the principal acid species is the hydrated metal ion, hexaquo iron plus 3. I don't care about its name. Its formula tells us really all we need to know. So this ion in aqueous media, for the analysis we began with last time and will now complete, is represented as Fe3 plus, quote unquote. So I don't have to keep writing this long formula all the time. What do we recognize? A hydrated metal ion loses positive charge, H plus, favorably, because this is in keeping with Coulomb's law. Because if something plus loses something plus, and in so doing becomes less plus, but still plus, hey, that's coulombically favorable because like charges repel each other. Now, what's the main consequence of this from our analysis standpoint? The main consequence is that when we look at the second ionization equilibrium for this solution, which is established when quote-unquote Fe2 plus, which you recall is the conjugate base of this thing, but which in fact in this system behaves as an acid, Ka for this, pretty doggone close to Ka for the parent acid species. Upshot, if we are going to correctly calculate the hydronium ion concentration for a solution like this, you got to pay attention to both of these ionization equilibria. That creates a difficulty from an arithmetic standpoint, from a calculation standpoint, because we will now, just based on these two equations, recognize this is an unknown, this is an unknown, this is an unknown, and this is an unknown. We don't know what these molarities are. So we got two simultaneous equations so far written which contain four unknowns. And as you know from algebra class, this cannot be solved. We have to develop at least two more simultaneous independent equations composed of the same set of unknowns. Then we can solve. And if nothing else, we reminded ourselves last time that this stuff is pale violet, this stuff is yellow-brown, and Fe single plus is also yellow-brown. If you observe this solution in the laboratory, you'll see that it's yellow-brown. The observation itself is telling you there's appreciable conversion of this to this. And our conversation has reminded us there's also going to be appreciable conversion of this to this. This is a rather substantial K value. This is a fairly low molarity. Have we not recognized from percent ionization considerations? When you got fairly substantial K values and low molarities, ionization extents are appreciable for weak acids. That's what we got. So we wrote this here. Both Ka1 and Ka2 for Fe3 plus, quote unquote, contribute to the hydronium ion concentration. So as things stand, we can't solve for the hydronium ion concentration because we got four unknowns and only two equations. So we got to get two more equations. Well, one comes to us from a consideration we came to recognize earlier on. It's called material balance. So here's material balance for all the various forms of iron in this system. M sub I, the label on the bottle, has got to be equal to the sum of the equilibrium molarities of Fe3 plus, quote unquote, Fe2 plus, quote unquote, and Fe plus, quote unquote. Because these constitute all the possible forms of iron in this solution. And now how do we get our fourth equation? We get it from really a very fundamental consideration based on, guess what? Coulomb's law. It's called charge balance. A bulk-cess chemical system which contains charged species, and any water solution is such, if for no other reason, because any water solution will always contain a measurable molarity of hydronium ion and hydroxide ion, and those are charged species. Charge balance says, as Coulomb's law dictates, in order for a bulk chemical system which contains charged species to be stable, it must be electrically neutral. That means You've got to have an equivalence between moles of positive charge and moles of negative charge in the system. That's the only way it can be electrically neutral. That allows us to write the fourth equation which we need, charge balance. I'll tell you a story about this. You know I like stories. Many years ago, 1967, when I started here as a graduate student. Because if I haven't told you, I have my PhD from here. I was teaching 46 Laboratory, which most of you are presently enrolled in. And the student was doing assignment 2, a student in my bunch was doing assignment 2, and was directed to perform a flame test analysis on sodium ion. You've all done this, haven't you? Okay. Well, I noticed this student getting rather upset as he traveled from reagent shelf to reagent shelf. I didn't know what was wrong. So I inquired. He says, I'm supposed to do a flame test on sodium ion, and I can't find a bottle that's only got sodium ion in it. I thought. So I told him a story. I said, the only way you make sodium ions is to get sodium atoms, which are electrically neutral, to lose 1 electron per atom and become Na+. Well, he understood that. And I said, if you could run this reaction all by itself and get this bottle that just had sodium ions in it, then it must be true that you could also have collected the electrons. So I said, I'll tell you what. If you can figure out how to do this, you get the sodium ions so you can do your flame test. Me, I'm going to bottle up all the electrons. And then I'm going to have a store. I will found a store. Horvath Electron Store. Shop, whatever you want. And I'll have these electrons in bottles or jars, whatever. And people will buy from me bottles of electrons, and they'll go home. And they'll go to the socket on the wall and put a funnel in the socket and open up the electrons and pour in the electrons. And the radio will radiate, and the television will televate, and the toaster will toasterate, and all the electrical devices will operate, and I will get on the phone and call up GRU and say, go to hell, I do not need you anymore. But there's a problem. You can't do this. You try to put a cluster of like-charged particles in the same vicinity as they would obviously be if in this jar you only had sodium ions. You would have something, a system which would explode with such potency and wipe out Gainesville. I'm sure. Can't do this. So, with this, I reminded the student that if you simply get some sodium chloride or sodium chloride solution or sodium nitrate solution, what have you, you'll have a system that fills the bill because it's a system with sodium ion in it. With the additional reminder that the anions do not cause any coloration of flame in the visible region of the spectrum. So if when you do the flame test you see a color, it's because of sodium ion. It's really because of sodium atom. It's another interesting part of that, but that's more physics than it is chemistry, so we're not going to bother with that. So on this basis, for any system which contains charged particles, we can write a charge balance equation, because the system has got to be electrically neutral. And for this system, we know because we have learned how to make inventories. That for this system, the positively charged species are Fe3 plus, quote unquote, Fe2 plus, quote unquote, Fe single plus, quote unquote, and the thing in which we are principally interested, specifically hydronium ion. And the negative charged things in this system are nitrate ion and hydroxide ion. And we take advantage of the fact that we know nitrate ion to be the conjugate base of the strong acid nitric acid, so we know nitrate ion has no impact or bearing on pH, hydronium ion concentration. So I write hydronium ion molarity plus 3 times Fe3 plus molarity plus 2 times Fe2 plus Fe plus equals nitrate ion plus hydroxide ion equals 0.030. There's our fourth equation. And this numerical value, which is equal to the charge balance equation, is called a charge sum. Now comes the fun part. How many of you understand how to write this equation? I just put it on the board. It's in the notes. Do you know how to write it? Never mind. How do we write it? Take note that each molarity has a multiplier in front of it, a multiplying coefficient, which is equivalent to what property of the species? Charge. That's it. 3 times this molarity, 1 times this molarity, 2 times this molarity, and blah, blah, blah. So then you might ask, well, why the heck is that true? Let's look at a much simpler case, and I think you will see at a glance why this is true. I ask you to write charge balance equation for the principal species in calcium chloride solution, 1 molar. Now the principal species in this solution, which are charged, because obviously charge balance only applies to charged species, not the molecular species. They don't have charge. Calcium ion, chloride ion. Nothing fancy about that. Now we look at the label on the bottle. For this solution, what is the calcium ion molarity? The calcium ion molarity for this solution, what is it? 1 molar. And we don't have to write an M because the square brackets say we're talking about molar concentration. What's chloride ion molarity? 2. Nothing fancy about this, is there? Now then, how do I establish an equivalency between these molarities? I got to multiply this by 2, don't I? 2 times 1 equals 2. That's it. And 2 is the charge on calcium ion. That's it. It's all done. That's how this follows. So, I contend that writing a charge balance equation depends on your ability to inventory, and that we've worked on now for a long time in depth. So you ought to be able to do that. And taking a look at the charge on the species and multiplying the molarity of that species by that charge, that's it. Neglecting sign. We just take the absolute value for the charge. So we had a -2 ion, a -3 ion. We just multiply by 3, not by -3. That's it. All done. Now, do you also see for this system where the charge sum comes from? Charge sum is 0.030. Where's that come from? You see the solution? And you see the numerical label on this solution, the M sub I value? What's the nitrate ion molarity in that solution? Isn't it? 0.030. Well then, we know the nitrate ion is in there. We know that it doesn't participate in any acid-base chemistry, even though it's a negative ion. And we know its molarity is 0.030. So that's a charge sum. Done. Do you think it's fair for me to say that if for this solution After I determine such, specifically the hydroxide ion concentration, you think it's fair for me to say that the hydroxide ion concentration added to 0.030, which is the molarity for nitrate ion, is not going to change this number? Is that a fair statement? What kind of solution is this from a general pH categorization standpoint? Is it acidic or basic? It's acidic, isn't it? You got two acids in there, don't you? So the hydroxide ion molarity, whatever it is less than 1 times 10 to the minus 7. And if I had something that's less than 1 times 10 to the minus 7 to 0.030, I guarantee I ain't changing 0.030 at all, nothing. That's like the whisker from a flea landing on Jupiter. Would you argue that the mass of Jupiter equals the mass of Jupiter plus the whisker of the flea? Would you believe that? I'd hope so. I guarantee, if you work in a circus and measure the mass of your largest elephant, and then you touch the elephant and in so doing put your fingerprints on the elephant, you're not going to measurably change the mass of the elephant. You agree with that? Wonderful. All right. Before we proceed, let's try a little bit more detailed consideration. Aluminum sulfate solution, 10th molar to 2 sig figs. Write the charge balance for principal species. Do that right now. Let's go. On your paper, let's go. Do it. Oh, this thing keeps falling apart. Because, as with all endeavors, the only way to learn it is to do it. Principal species, this solution. And of course, charged species is what we're talking about. What is the principal positively charged species? What's its formula? Did you write that? That's it. Principal negative species in this system. Sulfate ion. Molarity of this? 0.20. Molarity of this? 0.30. Multiplier? Oops. Multiplier. Charge magnitude. Is this charge balance equation for principal species in our aluminum sulfate solution, 10th molar, can this be equated to a charge sum? If so, what's the value? I want the charge sum right here. What is it? 0.6. Nothing fancy about this. My golly. We know the sulfate ion molarity is 0.30. Twice that is 0.60. Aluminum ion molarity is 0.20. 3 times that is 0.60. Done. Now, if I ask you to write the all species charge balance statement for this system, what would you write? Now you ought to have a good idea on how to do that, since we've got the all species charge balance equation here written for our iron nitrate solution. And I should hope that you'd recognize that hydrate aluminum ion is going to show a behavior a whole lot similar to this. Are these not each hexahydrates of +3 metal ions? Hey. Now it is true that hydrated iron +3 is a lot stronger acid than hydrated aluminum +3. We'll talk about the impact of that on this system in a moment. But if we're going to write the complete charge balance equation, we'll leave this up here. Any more plus things? Hydronium ion, of course. Any more minus things? Any more minus things? What is it? Yeah! What is it? Hydrogen sulfate ion. Charge sum. There it is. So, we got the whole 9 yards written for this. Now, if we set about the task of calculating the hydronium ion concentration for our iron nitrate solution, we know that this be true. We know that in doing the analysis we really don't care about this. I'll take this out right now and put in this, because that's what this molarity is equal to. And if I wanted to keep this in, would that constitute another unknown? Yes or no? I saw heads go. So I go like this. What are we saying? Is this, yes or no, another unknown in this system? The answer is hell no. If you know the hydronium ion molarity, then this is Kw divided by the hydronium ion molarity, isn't it? Now then, do you think in solving for the hydronium ion molarity for our iron nitrate solution, we could forget this term? I think it would be legitimately negligible. Well, we start by knowing it's less than 1 times 10 to the minus 7. How will the hydronium ion molarity compare to this number? Well, you could say, well, it's bigger than 1 times 10 to the minus 7, but that's not saying a whole lot. For this system, the iron nitrate solution, tell me how to calculate. Here it is. Hydronium ion concentration minimum for this solution.
K1 plus x squared
Done. Did you hear what he said? I operate on Ka1, and to get this, I neglect Ka2. Because I know that whatever I get as an answer for this, the true hydronium ion concentration for the solution is at least this, but most likely bigger, and a good deal bigger, because I've already recognized that the second ionization equilibrium for this is going to contribute measurably to the hydronium ion concentration. All right? So, when I want to do this, I would write, well, here, let's put it over here. We've done this part. (4.0 times 10 to the minus 3 is x squared over m sub I minus x. And I'm going to put quotes on this. I put quotes on this because the value this is going to give me for the hydronium ion concentration will be this. And our Horsens tell us that will not be the hydronium ion concentration for the solution. But it will be the lower limit value if I want to set up a boundary, a range for the hydronium ion concentrations for this system. So, if I operate on this, given that m sub I is this, I'm going to have to maintain x in the denominator to solve this correctly for this system, because Ka is rather substantial and m sub I is a small number. And you know how to do this. What did I get? I got something here. 3.9 times 10 to the minus 3. I think that's right. You can check it. So we'll start by knowing that the hydronium ion concentration for this solution is guaranteed to be not smaller than that number. And our Horsens tells us it's bigger than that number. How big can it be? What's the upper limit value for the hydronium ion concentration for this solution? Well, if the first ionization goes 100%, you agree that corresponds to upper limit value? First ionization goes 100%, what would be the hydronium ion concentration? What would it be? I started out with 0.010 molar Fe3 plus, quote unquote. If that goes 100%, that gives me a hydronium ion concentration value of 0.010. But the second ionization also goes 100%. Then I got a hydronium ion concentration upper limit of 0.020 done. So, before I do any arithmetic on this system, I got hydronium ion in a good box, don't I? I'll write that down. In here someplace. And for whatever it's worth, I've not yet taken the time to calculate the actual hydronium ion concentration for this system. It doesn't matter. What counts is to realize how to do it, and that's what we've been talking about. So, do you think, with this being recognized as a hydronium ion concentration min for this system, I can throw this away? This is on the order of 10 to the minus 10. That's nothing. Forget that. Now look at this. Now for this system, before we proceed, I also ask, what's the principal acid-base equilibrium in this system? The principal acid-base equilibrium. The answer's got to follow from our inventory, doesn't it? It can't come from any place else. In this system, the strongest acid is, in appreciable molarity, hydrated aluminum ion, isn't it? And in this system, the strongest base is, in appreciable molarity, what is it? It is not? What is it? Sulfate ion. Isn't that a stronger base than water? Isn't that a principal species in this system? Well, so our main acid-base equilibrium in this system is hydrated aluminum ion reacting with sulfate ion, making quote-unquote Al plus 2 and hydrogen sulfate ion. But we cannot use that equilibrium to get a handle on pH because it does not contain any pH terms, specifically hydronium ion or hydroxide ion. If we are assigned the task of calculating the hydronium ion concentration for this system, do you think it's a fair bet that we might not have to pay attention to Ka2? A fair bet that we might not have to pay attention to Ka2 if we have the task of calculating the hydronium ion concentration for our aluminum sulfate solution. We've analyzed the iron nitrate solution to conclude, yeah, we got to pay attention to Ka2. That's why we needed the two other equations. Oh, what's different? M sub I is 10 times bigger. That means ionization extents for this system will be, compared to this, smaller. And if you look at the acid-base table, you'll see that Ka for this thing is 1.4 times 10 to the minus 5. That's a good deal smaller than 4.0 times 10 to the minus 3. So before we do any arithmetic on this system, we start by knowing that the ionization extent of hydrated aluminum ion is going to be a hell of a lot less than the ionization extent of hydrated iron plus 3. So that means it is possible that the correct hydronium ion concentration for this system can be calculated by not paying attention to this or this. It's possible. But you have to do the analysis to prove it to yourself. It's all right. No big deal. What counts is that we now know how to do it. Now, you know about the extent of this equilibrium? Tell me. How small? 0.00%? 1% small? 10%? 20%? Let these numbers that you just looked at, the numbers you see in the acid-base table, let these numbers talk to you. Without doing any calculation, I want you to give me a reasonable approximation for the extent of this equilibrium reaction. Left or right is written. Tell me. What do you say? I want extent. That means a percent. 10%? 90%? 10 minus 8%? Have you not recognized that Ka ammonium ion and Ka HCl are very close to each other? Right? About 50%. Not quite, because Ka HCl is a little bit bigger than Ka ammonium ion, right? This thing goes almost 50% prior to the establishment of the equilibrium condition. So, unless you know the extent to which this proceeds, you can't set this charge balance equation equal to a charge sum. Because when this reaction occurs, I take charged things and turn them into uncharged things. So unless I know the extent of this, I cannot write the charge sum value for this. All I can say for sure is that it will compare how 0.10. Smaller than 0.10. And if I recognize that this goes about 50%, it'll be about half of 0.10. But until I get the percent of that nailed down, I can't say for sure what the charge sum is. We'll talk more about this in a minute.